Swayam Prabha. Digital India. Educated India.
Hello and welcome to the course on Foundations of Cyber Physical Systems. So, in the last lecture we have been talking about hybrid automata and different kinds of models. For example, we took two examples of leaking gas burner, bouncing balls, some of those nice and simple examples. So, today we will be starting with an example of first a formal definition of how multiple such automatons can be composed. Okay. So, let us see what it means. So, suppose you are given this kind of two hybrid automatons. Again, this definition has been taken from this book, as you can see. Okay, I mean, of course, it is a standard definition, and different books you will find it in different flavors. So, let us say we have hybrid automata H1 and H2. For each one, you have Q1, X1, the flow function F1, the initial state init 1, invariant state inv1, E1, G1, R1 with the etc. And similarly for H2. And they have two alphabets, sigma 1 and sigma 2 for their input events. So, now we are considering an automata where the event transitions will be having guards, resets and also an input event, okay, which was not part of our initial definition, but we said that they always are there, in different classes of automaton. So, when I compose these two automaton, we will have a set of states. If you remember our discussion of finite automata, and we compose them for the intersection automaton when we created them. In a very similar way, the composition of is a hybrid automata which is given like this. It will have a set of locations given by Q1 cross Q2, where Q1 and Q2 are the original set of locations, right. And you have this set of real valued valuations, which will be just x1 union x2, because the valuations of both automata will come in. Your set of symbols will also become a union, and then you will have this set of these flows, right, and the flow set will be an intersection. We will explain with more why this is so with some example, why the flow has to be an intersection, etc. And your initial states will also be an intersection. That means you will start with initial state of both of them, and your invariants, since you are composing the states, the invariant conditions will also get composed. Okay. Now, what about the transitions? So, this is how we will have the transitions. If you have this state Q1 comma Q2, like it is a tuple, and with an input sigma you are jumping to a state Q1 prime Q2 prime. When is this possible? It is possible under these three conditions. In case this input event is a part of the input alphabet of both the component automatons, and then if in the first automaton for the input event sigma and starting from state Q1, I am supposed to jump to some state Q1 prime, and in the second automaton similarly from some Q2 I am supposed to jump to some state Q2 prime, then here I go to Q1 prime comma Q2 prime. But the more other cases, non-obvious cases are, suppose the symbol is a part of only one of these input symbol sets, suppose it is not in the second set, that would only mean I will follow simply the transition function of the first automaton. That means I will just follow the Q1 sigma Q1 prime, this transition. So, from Q1 I will move to Q1 prime, and this Q2 is basically same as Q2 prime. So, the second element in the tuple will not change. Okay. And same thing for the other case, that means this sigma is not there in the first symbol alphabet, but it is in the alphabet of the second automaton. In this case, you will follow essentially the transition function of the second automaton. So, then your Q1 and Q1 prime are same. So, you are not changing in the first component of the locations, but only the second component of the location is changing from Q2 to Q2 prime. Okay. And that is what is being captured here. Now, what about the edge, the guards and resets? So, suppose you have any edge Q1 Q2 to Q1 prime Q2 prime, you have any edge like this. Now, if you have your guard will be like this. So, it will just be a combination of G1 and G2, where G1 and G2 are the individual guards of the transitions from Q1 to Q1 prime and Q2 to Q2 prime. Similarly, you have reset condition as a combination of R1 and R2. Okay. Now, this will happen when your symbol, your alphabet, your element sigma, your input element is a member of both the alphabets sigma 1 and sigma 2. If it is the case that sigma is a member of only sigma 1 or sigma is a member of only sigma 2, then it is different. If it is a member of only sigma 1, then the guard condition will only be G1 and the reset set will be R1. That means, in principle, since it is just being recognized by first automaton, so you are following essentially the transition of the first automaton itself, and the second component remains same. Okay. Similarly, if it is the component of the first if it is not a member of the first automaton, only the second automaton, then you are just following the guard and reset of the second automaton and the first component is remaining the same. That is what it will just mean. And now, the important thing is that if it is a common event, then the transition has to be agreed upon by both the individual automaton, like we just said that if it is sigma 1 belonging to both the alphabets, then the guard and resets must be satisfied by both the automatons. Okay. And the other things are what we have just said. Now, coming to the flow condition or the vector field. So, if x belongs to these two, I mean you pick up any common variable, right, which is a member of both the automatons. Okay. And if the invariant condition, if it satisfies the invariant condition of both the automatons, that means we are talking about a variable, continuous variable, which is a member of both the automatons and it satisfies the invariant condition of the individual locations of both the automaton. That means this condition, this intersection is non-null. Then what must be happening is that this is a common variable, right. So, it cannot at a time obey two physical laws, two different physical laws. It has to open only one physical law of evolution. Hence, although we have these two flow functions, right, f1 is the flow function for component automata 1 for this variable x for some state q1, f2 is the flow function for this automaton 2, right, for the same variable, right, for the state q2. So, when we are having this q1 q2, this combined state, xi, this variable must have this common flow function. So, these flow functions must be equal, right. So, in this way, this combination, this kind of synchronization events or some such common events and composition of hybrid automata, what is the usefulness? The usefulness is you can combine small automatons or component systems and build a larger system. Similarly, you can model a larger automata by breaking it into smaller modules and their communication. So, let us take an example. So, what we have here is we are considering a train which is kind of moving in a circular track, okay, and from some point y equal to 0, we are measuring the distance covered. Let this be the distance values y equal to 5 and y equal to 15. So, this is a circular track where the train is moving. Okay. When this value of y is between 5 and 15, okay, in this region, okay, we will say that the train is far away from the gate. So, it has left the gate, okay, and that it is just following the dynamics of the train itself is given by y dot equal to f y. And when it has reached this point y equal to 15, the gate must be closed, okay. So, this represents, I mean, so the kind of the train automaton, the train and its controller automaton is sending a signal that gate must be closed when y equal to 15. Well, for the train nothing changes, it is following the same its own flow function. Only thing changes is that this state, this location and the other location, they are differing, because this when I am here, that means I have sent the signal that you close the gate, and when I am here, it means I have sent the signal that you open the gate is sending an up signal. So, when I am here, the only invariant I have is y is between the overall value of 0 to 25, that is the overall track length here. Okay. And fine, and when the train is I mean kind of out at this point y equal to 5, so it sends this up signal to the gate. Okay. Now, this is my automaton for the gate. When it gets an up signal, the gate has a continuous variable which is kind of denoting, let us say this is my gate, and it's denoting the height of the gate, right. So, when it gets a signal down, x must have a negative I mean negative differential. So, x dot is 1 minus x by 2, something like that, which gives me a negative value, and the gate will come down. When I am getting initially, so the initial condition is x equal to 1, right. So, when I mean the gate will eventually lower down here. Okay. And then when it is up, the up signal comes. So, this is the flow vector now 10 minus x by 2 etc., which will ensure that this is positive and the gate will finally go up, right. So, that is how these two different automatons are conducting themselves, and if I am going to kind of combine them, that is the combined location of train plus its controller and the gate. So, that is the dynamics of the train. This is the dynamics of the gate, that means you are signal the gate to come lower down. So, this is the composed automaton, as you can see. So, in each of the states you have the train approaching the gate, and it has this is the synchronization of the states, right, because based on the common events it has been decided which of the states can be together and which of the states cannot be together. So, the train is when the train is near, it has already signaled down to the gate. So, this is one admissible state, and when the train is further, that means it is satisfying y equal to 5. In between that place y equal to 5 to 15, in between it is kind of in the left state, and the gate is rising up, right. So, and the train dynamics, the gate dynamics, and the invariant of this condition, right. So, that would be the composed model in this case. Now, once we have discussed this of the issue of composition, the next important thing to decide is what about, what is the execution semantics of a hybrid automata? How do I formally define a run of a hybrid automata? If you remember, we talked about a run of a finite automaton, that it's a sequence of input events, but here we also have this notion of real time, right? So, for a hybrid automata, we talk about a time trajectory, and it is nothing but a collection of consecutive real intervals. What is happening with a hybrid automata is that I am spending a continuity of time in different discrete locations, right? So, that gives rise to a set of real intervals, and for each interval the system is in a fixed discrete location. Then there is a location switch and I am going to another location, there again a real interval is being spent, and then there is another discrete jump, I go to another location. That is how it is, right? So, it is like a sequence of intervals like I1, I2, I3 we have here, right? And for every such interval ij, it is basically like this. There are two real time points, tau j prime, right? And this interval is a subset of the real set, right? And the next interval is I j plus 1. So, it is starting from tau j plus 1 up to some point tau prime j plus 1, right? And what happens is this tau j prime is equal to tau j plus 1, which is the, so the end point of the ij must be equal to the start point of the next time interval, the next real time interval, which is I j plus 1. So, that is tau j plus 1, and tau j prime is equal to tau j plus 1. Okay. Now, there are these related operations. One is this prefix operation. So, first of all, then what do we have? So, we have a time trajectory. To summarize, it is a sequence of these intervals, right. Now, once we have a sequence, we can define prefix of a sequence, right. So, a prefix is defined like this, tau is one time trajectory given by a sequence of intervals I1, I2 up to In, right. And let us take its prefix as another set, set of time trajectory, another sequence of intervals tau prime, which is up to some m, I equal to 1 to m, right. So, this is another set I equal to 1 to m, right. And we will say that this tau is a prefix of this set tau prime in two cases, either they are equal, tau and tau prime are equal, or tau is finite and the number of indices, that means the number of intervals in tau is less than equal to the number of intervals in tau prime, and each of the intervals in tau, this I is exactly equal to the intervals you have in tau prime up to this value n. Okay. So, the intervals in tau let them be I1, I2 like this, the intervals in tau prime let them be I prime, these are primed here like that. So, we will say that this is exactly a prefix, then if whatever are the intervals in tau, they are all present in tau prime in that sequence only, and after them there are some more intervals. So, that is the definition. Now, we have another thing called the index set. So, index set is given by this. So, this collection of intervals that we have. So, this is my tau, right, and the number of such switches that we have, that means the number of intervals that we have, it is given by this set, the index set. So, if there are n such intervals, the index set has values 1 to n, if n is finite, and if this run has got infinite number of such consecutive intervals, then the index set is nothing but the set of naturals, right, because it is up to it is just continuing infinitely. Now, what is the length of a time trajectory? Length we can figure out simply by adding of the consecutive intervals real values, right. So, if this is the set, right, the consecutive sequence of intervals, then you take each of them from the index set. The index set is given by this L angle tau right angle, right. So, it is containing this the indexes, right, 1, 2, 3, like the indexes of each of these intervals. Now, for each of these indexes, you have the finish time and the start time. So, this subtraction gives you that interval value, you just sum it up. So, that will give you the length of the run of the hybrid automata or the time trajectory. Okay. So, overall we can define the execution of a hybrid automata like this. It is a collection. First you have the collection is a 3 tuple. First you have the time trajectory tau. The next you have is a mapping q from the index set to the set of locations, which tells that well inside this time trajectory each of those intervals I have spent in which of the locations, that is what it tells. And then I have x. So, what is x? It is a collection of the differentiable maps. That means it is telling me that inside each of these intervals, inside the time trajectory, you see I belonging to the index set, right? I belonging to the index set. What were the flow functions that I have followed, right? So, that is why those are the differentiable maps. So, what are the flow functions that I have followed for each of the variables inside each of the intervals? Okay. So, they are given by that. So, they would be like defined like this. My initial state is this q1 x1, right. So, I mean what is my location and what is my current for this location, with what flow function I am starting, that is my initial location. And then for each of these intervals tau I to tau I prime, what is the flow function that I am following, right. So, there would be something of this form, right, that some location I have this xi dot, right, and for each for that ith interval I am following some flow function f and I am in some state q I, right. So, you see I mean everything is algebraically defined here quite nicely. So, let us say I am in the second interval, right. Inside this sequence of intervals tau, I am in the second interval. So, I value is 2, right. So, I value 2 means what do I really have? I am trying to figure out what are the flow functions being followed, right. So, the flow functions would be very simply figured out like this. F is nothing but I will then check with this function q for the value 2. It will give me a location. So, q2 here will give me a location, that where I am in that second interval. So, that is my q2, that is my location. In that location for each of the variables I will have the flow function defined, and that will be my differentiable map xi dot here, right. That's it. And then another interesting thing is, for all these i's that are in the index set, I mean minus the final one, except the I mean this minus the final one means all the switching indexes I except the final one, in case n is finite. Otherwise, if it is infinite, then there is no final one, there is no meaning of minus n. Okay. So, in that case we have a set of edges and they are defined by like this, right. You start from the ith indexes location to the I plus 1th indexes location, right. And for each of them you have their corresponding. So, this will give me the edge which I took for going from the ith interval to the I plus 1th interval in the time trajectory set, right. And this would be my corresponding guard condition, and of course, this would be my corresponding reset condition. Now, how do I get these times? So, it is very simple. So, we are talking about the ith interval, right. So, II. So, if you remember, II starts with tau I and it ends with tau I prime, right. So, at the start tau I am going to have this interval, right. This is I mean at the end of this I am going to take this transition, right. When I take this transition, I should be at the time I should have a valuation or my mappings. I mean at this time instant tau I prime, my vector fields must be giving me suitable valuations of the real values, so that this guard condition is satisfied, right. That's the point. And not only that, once I take this transition, I get to the second interval set, right, tau I plus 1, tau I plus 1 prime. So, now I am at tau I plus 1, I am following the next set of differentiable maps x I plus 1, right, and they must belong, that means they must satisfy the reset set of this transition. So, I took this transition E, right, and while I took this transition, I satisfied this set, I mean this set of valuations for the map, right. So, whatever is the reset condition here, that must be satisfied here, right. So, when I take this map, when I go to tau I plus 1, that means the next time instant in that next target location. So, wherever I am in wherever I land up in that location, then I would have a differential map which should be belonging to this reset set. That means, in that H set what is the reset set, that I should be there. So, here let us take a simple example. So, let there be these two tanks. They are filled up with water, and this is the reference value of water. That means, the water level at all possible time must be above this R1 and R2. In this one, that is tank 1, and this is tank 2, and the actual water level that be given by some x1, and here it some x2, and they are also having some outlets through which the water is also draining out at some pace V1 and V2, and there is an input pipe which can either be here or it can be here, okay, and that pipe has a flow rate W, and this switch can be controlled. You can control this location, okay. So, this is known as the two tank problem, okay, and so the thing is, you have to have a suitable control law to control the location of that inlet, and you have your, that is your control, and the control problem is that you must have x1 greater than R1 and x2 greater than R2, okay. Now, what should be your control strategy? So, let us say your control strategy is that you switch the inflow to tank 1 whenever kind of x1 goes below or x1 is equal to R1, and you switch the inflow to tank 2 whenever x2 goes below or x2 is equal to R2. Let that be the control strategy, okay. Now, if we try to identify a hybrid automata for that, let us see how it turns out. So, it is basically like this. So, this state designates that the water flow is towards I mean tank 1, and this state means that the water flow is towards tank 2. So, when the water is flowing towards tank 1, you have a net positive water flow, assuming that W is greater than both, we are assuming that W is greater than both V 1 and I mean W is also greater than V 2. Okay. So, you have this, that this is net increasing, the tank 1 value is rising, but of course, the tank 2 will be going down, and you have a location invariant that tank 2 is still having some value greater than the reference. Whenever it is less than the reference, you switch the flow. That was by control strategy, remember, that is what we discussed. So, you switch the flow here. So, to x1, now what happens is tank 2 will have a positive gain, and tank 1 will have depleting water, and similarly we have a condition that I can only be here as long as tank 1 where I have depleting water does not deplete fast enough and go beyond R1, because whenever that happens I again switch the flow. Okay. So, that is the condition. Now, so that is about it. Now, let us assume that W is such that yeah, let me write it down, W is less than V 1 plus V 2. So, if this is so, then what is the expectation? The expectation is eventually, I mean my net inflow is less than the total outflow. That means, whatever I do, whatever is my control strategy, eventually both the tanks will run out of water. That is going to happen, right. So, let us see if the simulation of this situation really leads to that. Let us see that. So, you see, suppose I started somewhere here. So, here I am plotting both the values x 1 and x 2, right. So, initially I am filling up tank 1, right. So, tank 1's value is rising and tank 2's value is going down. So, I am following this. Somewhere what will happen is tank 2's value will be very small, almost touching R2. So, here the control will switch, right. So, this is the condition we have assumed, like I said, that the total inflow is less than the total outflow. So, when the W tank 2 has depleted almost to R2, then it will switch, and now what will happen is tank 2's I mean water level will rise, but since tank 1 does not have a supply, it is decreasing, right. Again I will switch, again I will switch. So, you see, whatever we thought that eventually the water in both the tanks will deplete, that is happening, but the problem is I am not going to 0. I am going towards this point R1 comma R2, which was not supposed to happen. Also, if you see, as I approach R1 to R2, R1 comma R2, the switchings become very fast, right. And if you think in the limiting case, what is happening is I am going to have too many switchings inside this finite amount of time. This is a finite amount of time, right. And here with the switchings becoming extremely fast, I mean I am actually going to have infinite number of discrete switches inside this small finite interval, right, which cannot really happen. So, this is known as the Zeno phenomenon. I mean the switches, because because this is something that it cannot happen in a practical world. I cannot have infinite number of switches inside a finite interval, which is happening here. So, this phenomenon is named after Zeno of Elea. Zeno of Elea, who was a famous Greek philosopher. So, it represents what a causal system cannot have, right. So, this hybrid automata happens to suffer from Zeno phenomenon, and there is a good reason. We are assuming that these switches are not taking any time, but for all practical purpose in a real tank, even this switching of the controls water inflow to outflow, they will take a finite amount of time. Since we are assuming them to be instantaneous actions, it is happening that here in this specific case, I am having such an exhibition of Zeno phenomenon, where we have so many infinite number of switches happening in a finite interval. So, there are techniques to remove them from automata. So, that is something you can study in the future in some advanced course. But what we only want to do is we want to make you aware that hybrid automata can exhibit Zeno phenomenon in some cases. So, if you remember in the previous few slides, we talked about execution prefix, right. Suppose so let us x be a time trajectory of the automata, where you have this sequence of intervals followed by this sequence of locations, intervals along with these locations and these switches in the vector field. And let us say this is a prefix of another execution, okay. It is denoted by this. I mean x is a prefix of x hat. If tau is a prefix of tau prime, that means all the intervals here are covered inside this, and in between for all these intervals, whatever has been the locations, they have remained same in both of the executions, and whatever have been the these differentiable maps, they have also remained same in both of the locations. So that's it, right. Now, a few more terminologies we will like to introduce is, so for such an execution of an automata, I will say that it is minimal, it is maximal if it is not a strict prefix of any other. Strict prefix means that there is at least one more interval in the larger sequence, okay. So, if there are no others who have one more interval in the larger with a larger sequence, then this is the maximal execution. It is finite if its index set tau, that means the number of intervals is finite. It is infinite if the index set is the set of naturals, that means I cannot find a final interval n whose its value, and the execution is Zeno if the number of switches we have is infinite, okay. That means the number of these intervals that we have is infinite, but if you remember, we also had a calculation of the total time, right. This was my calculation of the total time, that is not really so. So, this is a nice way to capture it. We are saying that the total time is less than infinite, I mean the total time is finite, it is a finite time duration, but the index set is infinite. So, this is kind of a mathematical way to capture the Zeno phenomenon. So, essentially we have infinite sequence of intervals, but the total time taken by the intervals is limiting, in a limiting case is approaching a finite value, okay. So, that is how we can mathematically characterize these different properties of automata's simulation or automata's execution, whether it is Zeno, whether it is infinite, that means and all that. So, just to repeat, it is maximal if there is no larger sequence, it is finite if I have a finite number of these intervals where it is staying in different locations. It is infinite if this index set is infinite, that means I have an infinite number of this sequence of intervals. It is Zeno if I have infinite number of this sequence of intervals, but their total time elapsed is finite, that is the Zeno situation. So, it can be this, I mean for Zeno it has to be infinite, but the total time elapsed is finite. And in a normal non-Zeno case, what we will have is, the non-Zeno case is whenever its execution is infinite, that means I have an infinite number of sequences in that set tau, the corresponding index set I mean is infinite, but the total time taken of the intervals is finite. So, the execution is infinite if both are infinite, that means that the total number of intervals is infinite and the summation of the intervals is also infinite, the time elapsed is also infinite total. Now, with some more terminology, so let us say this is telling me this is a set which gives me all the executions that a hybrid automata can have starting from an initial state or initial condition. Let us say this is a set of the total number of maximal executions, that means all the executions after which there are no further possible locations, okay. And this is a set which denotes the total number, I mean the set of all possible finite executions, that means the executions continue and then they end with some final location, okay. And these are the total possible number of infinite executions that are possible from an initial state, okay. So, just to remember these notations, because we will use them for some another definition, we will end it here. So, this is for all executions of the automata, okay. The second one is for all maximal executions, okay. The first one is for all executions, among them those who are maximal, they are in the set this zeta m, and this zeta star is the set of all those finite executions, and these are the infinite executions. Okay. So, we will say that a hybrid automata is non-blocking if the set of infinite executions starting from the initial state q 0 x 0 is non-trivial. That means, there exists at least one sequence of intervals which is, and that sequence is infinite. Okay. So, that is an infinite execution sequence. Okay. If that is there, then if we have such a sequence which is an infinite execution sequence, and at least one such sequence is there, then I say that the hybrid automata is non-blocking. That means, it does not block, I mean there is, I mean there at least exists a trace which is allowed to proceed, and maybe it is not happening that whatever trace whatever execution sequence the hybrid automata we make it follow at different possible locations at different possible times, it eventually blocks due to a guard condition or an invariant condition. It is not happening. There is at least one possible way for the execution to proceed up to infinity. Then we call it as non-blocking. And when do I call it deterministic? If I find that the maximal execution set has only one element, that means there is only one possible way starting from every initial condition. I start from every possible q 0 x 0 combination, and for every such initial state, if the hybrid automata has one unique execution sequence, that is what, right, that is what is this says, that I mean maximal means what, all the possible maximal, that means it is not a prefix of anybody else, there does not exist anybody else larger than that. Okay. That means here if that set is unique, that means there is only one possible trace, one possible unique trace, there is no other trace which is larger than that or whatever, and that is and it exists. So, this set is a singleton for all initial conditions, that makes it the hybrid automata deterministic. That means, I give it an initial condition, and and based on that initial condition there is exactly one possible way for the hybrid automata to proceed. That means, it will be in this location for this much time, then it must switch to that location for this much time, then it must switch to another location for this much time. That is a unique sequence. If it is so for all possible initial conditions, then it is a deterministic automata. And when do I say that it is a non-blocking automaton? We say that it is non-blocking if there is always at least one possible way for the hybrid automata to execute up to infinity starting from any initial condition, then it is a non-blocking automata. That means, there does not exist an initial condition from where the automata starts, and then whatever way it wants to go forward, it is blocked by invariant or guards, it is not happening. Then it is a non-blocking automata, it can always progress in some direction up to infinity, then it is non-blocking, and it is deterministic if its way of progressing is unique. Okay. So, these are the different kind of execution semantics of hybrid automaton, and with that we will end our lecture here today. Thank you.